In the first of the intro to multiple comparisons, we talked a lot about error, family-wise error, experimental error. I showed you a couple examples of how we get types of error, how we get to a certain quantity of error based on how many comparisons. So we have comparisons that we can do ahead of time, so we can sort of make a determination of how many things we want to compare ahead of time for multiple comparison procedures. Do planned analyses. Some of the planned type of analyses that we might do are orthogonal contrasts, effectively contrasts that don't overlap, or trend analyses, which are also typically orthogonal. I'm just kind of clicking down to those for a second. Orthogonal contrast, this was an example of orthogonal. When we cross multiply and add, we end up with 0 for those contrasts as one of the ways we can check. And trends are very similar, but they end up checking for things like linear, quadratic, and cubic trends. Here's what linear, quadratic, cubic trends, how many bends do we have in our trend? I want to come back to the idea of the actual multiple comparison procedure. I show you this, the standard T. It's in our textbook as well. It's the basic T. It's very similar to the basic T-test. Instead of using the pooled or some sort of standard deviation from each one of the samples that each one of the groups or subsamples that we care about, we're using the MS error for the total model. It's basically, you can think of this as like a more encompassing standard deviation or standard error of our data. So this is, I would expect you to go through this and the textbook, the examples for this. This is kind of the core analysis for the multiple comparison procedure. We can kind of see the numerator is this psi. This psi basically is the difference between the two groups or the contrast coding, and the denominator is the standard error. And I know I've gone over that in previous examples, and also the textbook does as well. I really want to talk to you more about some of the post hocs that we can do. Probably the most popular post hoc comparison is the Tukey test. It's considered the least controversial and uses all possible comparisons. You can see me in some of the SPSS videos use this, so I'm not going to do that right now. But basically, its family-wise error is computed based on all possible tests. We kind of, and if you were to do these by hand, you were to do a Tukey test. Here's the equation for this. It's the group 1 versus the next group means divided by the standard error, and here's the standard error. So, but basically, we just want to say, is there a difference? And we can kind of rank order these things and go from smallest to greatest to smallest differences to see if there is any effect. So we can also go look that up in tables in the back of our textbook. A slightly different statistic is Tukey's HSD, or the Tukey-Kramer multiple comparison. This is for post hoc comparison. So both of these, Tukey test and the adjustments, we'll see the Fisher test, etc. These are done after we have conducted our analysis of variance. So that's why they're post hoc procedures. We can just see that there's a slight adjustment here in the mean squared for our denominator. And we can do these for unbalanced groups. If it's robust to moderate non-normality. If we have a lot of issues with non-normality, we can use the Chaffee test instead. So another test is the Fisher's LSD. We basically only use this if it's looking at two-tailed pairwise comparisons, and we really only would use this if we have 3 groups to compare. And I wouldn't advise using it for anything more because you really don't have any control over type 1 error with this method. Our next one we are going to look at is the Denay test, the Brown-Ferroni adjustment. We basically have alpha split up so that it's less powerful. It's kind of a very simple and straightforward way of handling this. You can take an alpha of 0.05 and chop it up amongst the tests. There are non-parametric methods that we can use and their equivalents. I'll let you play around with SPSS with those for class. Just so you know that they're available, you can follow up with the Kurzweil-Wallace test for a non-parametric test, and those have a Chaffee and Tukey equivalent. In SPSS, I show you those examples, and this is our textbook. And also, I would refer you for power. I have a reference here for some power and weighted issues of some of their multiple comparison procedures. So I just want to talk to you about some of the differences and when to use them. There are procedures that when we think about, we can look at the House Vaughan text, whether you have the first edition or second, whether you have the first course or second course. I just want to go over a couple of these ideas and when to use those. So I'll kind of put it back on a slide with one of our more popular, the Tukey HSD test. In a figure in our textbook, I'm not going to use it now for copyright issues, but I will talk to toward that figure. So if you are in my class, you can look at the figure 2.2, which should be in chapter 2 toward the end on page 77. If you're not in my class, well, you can buy House Vaughan's text. Lomax is in House Vaughan text. They advise that when you start with considering which analysis to do, you start with, is the measure continuous? If it is, you may consider a trend analysis. If it's not, you may consider things like planned orthogonal comparisons, even a Dennett test. If it is not pre-planned, then we're going to have to first do our analysis of variance, and we will reject that analysis of variance. If not, we stop. We don't do any more comparisons, because if the analysis of variance isn't significant, it's our omnibus test, we stop. If we have many contrasts, we may want to consider doing one of the corrections, like a Bonferroni correction. If we have pairwise tests that we care about, we may have equal variances. If it's pairwise, we may consider going down to our Tukey or Tukey-Kramer rule. But if it's not, we may do a Chaffee test and look at equal or unequal variances. In SPSS, I believe there's also the Kaiser-Bowden analysis that we can do. For equal variances, if we do have equal variances, most people tend to go to the Tukey's honest significant difference, HSD, or the Fisher LSD if they have 3 less groups, whereas there's also the Tukey-Kramer adjustment if it's not equal variance, if it is not equal ends, If it is equal ends, we typically do Tukey and HSD. And then finally, if equal variances are not assumed, there's tests in there for SPSS, the Games-Howell, the Dennett T3, and the Dennett C. So again, if there's equal variances, yes, and equal ends, we use the Tukey test typically, and if they're equal ends, no, Tukey-Kramer. Unequal variances, there's several different tests to account for that. But in general, what I say is, there's so many different tests here that we can use when you go to SPSS. Most people will default to the Tukey test. I would just recommend thinking through the process, using our flow chart example that we have, and that's the process you should use. All right, I think that's enough for our sort of second video of multiple comparisons, and we'll follow up with some of this in our class.